Today's lesson is on polar kinematics, and it is taken from Tongue and Sheppard, section 2.3. Okay, so in polar coordinates, let me just draw some axes here. And we have an origin O and a point P at radius R and angle theta. So unlike Cartesian coordinates, where we have fixed unit vectors I and j, in polar coordinates we have unit vectors in the radial direction, ER, it is also a unit vector, notice the hat, and in the theta direction, E theta, hat. So the position of point P, so the position of P with respect to O, is simply R in the direction ER. And we'll just put a box around that. That is our position. Now, in order to find velocity of point P, that would just be the time derivative of the position of P. So R of P with respect to O dot. And that would be dt of R, our unit vector ER hat. Using the chain rule, we can see that that is, or rather the product rule, excuse me, R dot ER, well, that's straightforward, plus R, and this is the not so straightforward part, d by dt of ER. Well, that's a bit of an issue. Unlike in our Cartesian coordinates, where our I and j unit vectors are fixed, in polar coordinates, ER and E theta change with time. So we have to find the derivative of ER. So how are we going to do that? We're going to do that using the definition of a derivative. So let's make a section and call it differentiating ER. So the definition of a derivative, f prime of x equals the limit as x approaches 0 of f of x plus delta x minus f of x over delta x. Okay, so I hope you all remember that from calculus. So in this case, we want our x's to be time. This is a time derivative. So let's just rewrite that in a more convenient form for now. So we have df by dt is the limit as delta t approaches 0 of f of t plus delta t minus f of t all over delta t. And for convenience, let's take t naught is 0, t naught equals 0, and so t becomes 0 and delta t just remains delta t. So let's draw a picture of what's happening in this case. So if we make some axes here, and I'm going to show in red our initial R, so our initial position. So here's our position P. We've got unit vectors ER, and in green E theta. And in purple, we will make our position at some later time P prime with unit vectors ER hat prime and E theta hat prime. Notice that our R has also changed. As you will see later, that is not the change in R does not need to be taken into account in our calculations. And finally, we should note that this is theta, and this is theta plus delta theta. So this P is P at t equals 0, and this P prime is at t equals delta t. So another way of looking at the change in our ER and E theta is to draw them independently. So let's take E theta, and in blue ER, and then I will do in dotted ER prime, and dotted over here E theta prime. Okay, and the angle in between these is delta theta in both cases. Note that ER and E theta will always remain perpendicular to each other. These are unit normal vectors, so they always have to be perpendicular to each other. Likewise, ER prime and E theta prime are also perpendicular to each other, and we should remind ourselves that these are unit vectors with our little hats. Okay, so like I said before, we are just concerned with changes in ER and E theta. The change in radius does not affect our calculation. So let's find d by dt of ER. And we will call that ER dot hat. Okay, applying this to our definition of a derivative, this will be the limit as delta t approaches 0 of ER prime hat minus ER over delta t. So ER prime is our f of t plus delta t, and ER is our f of t. Okay, so we want to find ER prime in terms of ER and E theta. So how do we do that? So returning to this picture here in black, so we've got over here on the bottom, we have cosine of delta theta and sine of delta theta. This is just from trigonometry. And likewise, we have cosine delta theta and sine of delta theta. Notice that this sign is in the negative direction. So we can then write our ER prime, and that is equal to ER times cosine of delta theta plus E theta sine of delta theta. Similarly, e theta prime equals, notice the minus sign up here, so we have minus er hat sine delta theta plus e theta cosine delta theta. So we can write this in matrix form, and this is what we would call a transformation matrix. So we have er hat e theta hat equals matrix of cosine theta cosine delta theta sine delta theta minus sine delta theta cosine delta theta, and that is times our original er e theta. So this is what's known as a transformation matrix, or in this case, a rotation matrix. These rotation matrices come in real handy for 3D kinematics. But for right now, we are just focused on this equation here, where we have er prime in terms of er and e theta. And we want to do that. What we want to do is we want to substitute that into our derivative, which is right above it here. So we're going to take this and substitute in here. Okay, so let's do that. So we have er dot hat equals the limit as delta t approaches 0 of er prime, which is er times cosine of delta theta plus e theta hat sine of delta theta, and that is minus er hat over delta t. So we have just taken this equation and substituted in to our derivative for er prime. Now, we have an equation with delta t's and delta thetas. Since we are taking the limit as delta t approaches 0, and delta theta is the change in angle undergone during that time, we can say that the limit as delta t approaches 0 of delta theta is also approaches 0. Okay, so what does that allow us to do? That allows us to take some approximations where sine of delta theta, so the small angle approximations, so sine of theta is approximately theta, and cosine of theta is approximately 1. So then we can take our approximations. We'll do that in red. Over here, we've got cosine of delta theta, and that equals approximately 1. And we've got sine of delta theta, and that equals approximately theta. So let's rewrite our equation. We have er dot hat equals the limit as delta t approaches 0 of er hat plus e theta hat times delta theta minus ER hat, and that's all over delta t. So we notice that our ER hats cancel, and we are simply left with delta theta over delta t times E theta hat. Delta theta over delta t is the derivative of theta with respect to t, or theta dot times E theta. So our final expression is that ER dot hat equals theta dot E theta. And that is our, put a box around that, that is our definition of the derivative, the time derivative of ER. So now that we have our time derivative of ER, we can take that and we can substitute that back into this equation here to find the velocity of our particle. So the velocity of point P is a vector, and that is equal to r dot in the radial ER hat direction plus r theta dot, oops, I wanted to make my radial direction in blue, ER, excuse me, plus r theta dot E theta. And that is the velocity in polar coordinates. Okay, moving on from the velocity, we now want to find the acceleration in polar coordinates. So how would we do that? We simply differentiate the velocity. So d by dt of Vp, and that would be d by dt of r dot er plus d by dt of r theta dot E theta hat. So now we have to apply our product rule again. And so for the sake of clarity, I'm going to do this side in purple, and I'm going to do this side in pink. And just so we're clear on what terms come from where. So from this first term in purple, the ER term, we've got r double dot ER hat plus r dot ER dot hat, which we have already solved for. So we'll just underline that in purple so we know where it's coming from. And then we also have from our second term, we're going to end up with three derivative terms. We've got r dot theta dot E theta plus r theta double dot E theta plus r theta dot E theta dot. And we'll underline that in pink so we know where that has come from. Okay, so this is all straightforward. We already know what ER dot is. We solved that before. That's right here. but we have to find e theta dot. Now, we could go through that entire process that we just did using the definition of a derivative. However, there's a more simple way that we can take advantage of. So if we draw some coordinates here, and we say that this is, in blue, ER, and in green we have E theta. Oh, I forgot my hat over ER. There we go. And we know that the magnitude, that ER, the derivative of ER, its velocity, is in this direction. We know it's in the E theta direction, and we know its magnitude is theta dot. So we are going to say that the magnitude of ER dot hat equals theta dot. Well, we know that our basis vectors, ER and E theta, are always orthogonal to each other. So if ER is moving at a velocity of theta dot, that would mean that E theta is also moving at a velocity of theta dot, and that these velocities would be normal to their respective vectors. So we can say that the magnitude of E theta dot hat equals also theta dot. As for direction, we can note that this direction here is in the minus ER direction. So if we take ER, that's pointing in this direction, and this vector is pointing in the exact opposite direction. So we can say that E theta dot hat equals minus theta dot, because we know it has the same magnitude as ER dot hat, and it is in the ER direction. ER hat. Okay, that was pretty easy. Actually, I want that to be in black. There we go. And that is the definition of E theta dot hat. Now we simply have to substitute that into our original equation. We have AP equals R double dot, blue, R double dot ER hat plus R dot theta dot, green, E theta hat, and we'll underline this in purple because to show that it is coming from our first derivative term here. And then from our second term, we have R dot theta dot E theta hat plus R theta double dot E theta hat plus, now we can substitute in this term that we just found. So we have plus R, plus R theta dot times minus theta dot ER hat. And we'll underline this in pink. So now we have AP. If we collect our terms together, we've got R double dot minus R theta dot squared in the ER hat direction plus 2R dot theta dot plus R theta double dot in the E theta hat direction. And that is our acceleration in polar coordinates. If we look at these terms, some of them have some special interpretations. So this is our radial acceleration. This term is the centripetal acceleration. This term is the Coriolis. And this term doesn't have a fancy name, but it is the pure acceleration in the angular direction. I should note that you don't need to know the names of these various accelerations. Sometimes it's neat to think about, but fundamentally, remembering them by name, I find can be a little bit unhelpful. So I struggled with whether or not I was going to introduce the names to you here today. But that is the basic rundown of the derivation of the acceleration and the velocity in polar coordinates. So I'll label this acceleration in, and I will stop there.